But we want to get beyond that. And one of the first limitations you can notice in these models is that any of these rule-based or those kind of statistical natural language processing models of the 90s and 2000s still worked with words as symbols like hotel and laptop. And the problem with that is then we don't have any natural model of how words are similar to each other. So for example, in web search, if a user searches for Dell notebook battery size, we'd also like to match with Dell laptop battery capacity. Or if you search for Seattle motel, you'd like to match with Seattle hotel. And that's not something we get for free from symbols. There's no shared representation between these different symbols for words, even though they're similar in meaning. And so people have wanted to work to solve that. And a dominant idea has been this idea of distributional semantics, that you can learn about the meaning of words by looking at the distribution of context, the words in the context in which they occur. So if I want to know what the word laptops means, I can look for sentences that have the word laptops in them and look at the words in the context, often summed up as J.R. Firth's aphorism, "You shall know a word by the company it keeps." This idea has been reinvented in the context of distributed representation models by saying, well, suppose we represent each word as a high-dimensional vector. We can then have a high-dimensional vector space, and it'll turn out that words will be able to represent it in such a way that words of similar meaning will be very close together in that space, so that different verbs will group together and classes of verbs in the space. And this kind of representation has been extremely useful as a low-level meaning representation. It turns out you can build these representations in an extremely simple way. I think one of the things that's actually amazing about the success of deep learning is it's turned out that a few extremely simple ideas, almost unbelievably simple ideas, have turned out to have enormous power. So for this idea, we say that each word is going to be represented as a high-dimensional, real-valued vector. We are going to say that the probability of a word appearing in a context is going to be given proportional to the dot product of the vectors of the two words. And we say that our loss function is just going to be the extent to which we can't accurately give high probability to words that appear in the context of each other. And then we just have nothing else in the system apart from saying stochastic gradient descent, go off and fiddle around with the representations of these words. So you choose representations so that words that appear in the context of each other end up having similar word vectors so their dot product is high. It's sort of unbelievable that that could work as a way of learning word meaning, but it turns out to work incredibly well. In particular, what's interesting is it doesn't only put similar word meanings close to each other, there actually come to be directions in this word vector space which have meanings. So here you can see progression from positives to comparatives to superlatives of adjectives. And in the word vector space, there are pretty constant vector additions that can be done to move you from each of these forms. Of course, these word vector representations, or neural encodings as they're often termed, prove to be just incredibly useful for just about all NLP tasks. And so one NLP task is finding person names and organization names in text. And so if you just took what used to be the best kind of NLP systems for finding things like person and location names, and you said add word vectors to your system, that already gave you a very nice lift and you got several points in accuracy. However, we don't only want to deal with word meanings. We want to get beyond that into understanding the structure and meaning of text. And it's turned out that a totally useful starting point for that has been the idea of a language model. So a language model simply predicts what is going to be the next word that is going to be said. We see these language models on the surface every day. So if you're doing predictive text on a phone or you're looking at search completions on Google, those are language models at work. But language models have many, many other uses. So we use them in speech recognition, machine translation, text generation. Their uses go on and on. And so this has led into the first big class of neural networks that have been highly successful for natural language processing, the idea of having a recurrent language model. And the idea here is that we start with having word embeddings, but in addition to that, we have a recurrent state so that a new state is calculated above each successive word by taking the next input word, multiplying it by a matrix, taking the previous hidden state, multiplying it by a matrix, summing those, putting it through a nonlinearity, and that gives the next hidden state, and we repeat recurrently through the sentence. In addition to that, we can then predict what the next word is going to be, giving us our language model. And the way we do that is from the hidden state, we then put that through another matrix multiply and a softmax, and that gives us a probability distribution over next words. And again, what happens is we just say we're going to have a loss, which is the extent to which you give a low probability to the next word that actually occurred in a pile of text that we saw. And thereafter, we just say, go off and train this model by stochastic gradient descent to change all of the parameters in all of the matrices. And it works to produce a wonderfully good predictive language model of what words come next. And I'll come back to later how good are those models. We can use this to then generate our own text by sampling text. So we have the hidden state and a starting off point, and then we predict the next word, copy it down, use it as the input, predict again, copy that down, and keep along. And this gives us a generative model